Okay, very good. Can everyone hear me? Just nod. I can see a few people. Good. Thumbs up. Audio's good. All right.
So before you
So-
start, Mike, let me just
yes.
welcome everybody to our first real RaRa Academy session in a while. I am very happy to introduce Mike here, who will lead us through the FORNEC 2 presentation and helping us to learn about antenna modeling with FORNEC 2 over the next 4 months. And hopefully this will be the first series in a long run of successful RaRa Academies going forward. For those of you who might not be RaRa members, this is a good time to join up. We always try to give you interesting things to learn, and hopefully this is one of those things. Also, if you are interested in potentially teaching one of these RaRa Academies, I would encourage you to get in touch with us so that we can put you on the schedule. We are always interested in learning new stuff, and there's no subject too trivial to teach. There's always somebody who is interested in learning about that. So with that said, I will hand over the microphone to Mike. And if you have any questions along throughout the meeting, please raise your hand. I will try to watch the Zoom interface here so that we can interrupt and listen to your question and hopefully provide an answer. And with that, Mike, this is yours.
Okay, thanks, Carl. First, I want to thank Carl for organizing this, getting me a little comfortable with doing it and managing the whole meeting as we go through, and doing a little pre-work for it. Thanks, Carl. I appreciate your time and your interest.
You're welcome.
So very briefly, before we start working, I'll introduce my own role or perception. So this will be the first time I've taught a course on Zoom. I have taught for years. I taught process control to 5th year adults at RIT and chemical process control, which was a good class, a lot of work. But whenever you teach a class for the first time, like I'm going to teach here, and in a new format, it's going to be awkward at times. It's going to be perhaps slow at times, confusing at times, and I'll make mistakes. So as we go through, be mindful that this is the first time for us to do this, and in this format, which makes it difficult for everyone to talk and ask questions. So I think Carl wanted you guys, if you do have a question, to don't hesitate, but there's a little button someplace in Zoom down at the bottom, I think, where you can raise your hand, and then Carl will be looking for those, and then he'll give you the thumbs up for when you can ask the question. And I might also see it. I'm not sure. We'll see. But Carl sort of volunteered to do that. So if you do have a question, please raise your hand.
And you will find the raise hand function at the bottom of your Zoom window under the reactions icon. When you click on reactions, you get a bunch of icons, clapping, thumbs up, a heart, but at the bottom it says raise hand. And when you do that, as I'm just doing, it will show up in your icon that's associated with your account, and I can then take care of that. And I see that Rich and Peter figured out how to do other things with those reactions. So well done.
Peter, good morning. I like your reaction.
I don't know how to turn it off. Oh, it went off. Good.
Okay. So I'll go ahead and get started. My own background in 4NEC2 started in 2012 when I started building my own antennas, and I was very fortunate because I was completely ignorant about antennas for amateur radio, having started out in CB and bought a Radio Shack vertical, and that was my knowledge, which was zero. So when I started to build my own antennas, I got curious about the details of how they actually work and what's an effective way of building them, etc. And that led me to EasyNEC, which was for purchase, and then to 4NEC2, which was free at the time. And I thought, well, let me try this free thing. And that has led to a long love affair and many, many models built for many people. In my RDXA club, I've had many requests. I've modeled all of the antennas that we put up for our field day. And most recently, one of our members found an antenna from Europe, a spider beam, and we were thinking about acquiring a spider beam or a hex beam, and I ran all of the simulations that showed the spider beam superior and lighter. And oh, that might be me. 1 sec. Sorry about that, guys. At any rate, so there's a lot you can do with your club and with field day and with your own building of antennas as part of antenna simulation. I already showed this for those of you who attended. I'll skip that because you'll get used to that as time goes by. A brief introduction for people who weren't at the Wednesday talk. We're going to be using NEC2, which is free Fortran program from the Lawrence Livermore National Labs, but we're going to be using it through the eyes of a C++ wrapper written by Ari Voers called 4NEC2, which he meant FOR-NEC2, so he wrote that 4NEC2, and then he named it 4NEC2 in terms of its usage. Users will interact with the program NEC2 through a Fortran punch card API. Now, we're going to interact and build our Fortran cards in Notepad or Notepad++. If you don't have Notepad++ already installed on your computer, just Google Notepad 2+, right? All next, and then download it. It takes about 10 seconds to install, and it offers something you may find highly useful relative to Notepad. As you begin making changes inside here, you will make mistakes and you will want to go back to what you had before, but Notepad only allows you to go back one keystroke and then you're done. You got to think it out again. Notepad++ will take you back 100 keystrokes. I don't know how far. I've never had a situation where I couldn't keep going backwards. So if you make, 30 changes and all of a sudden you would like to go backwards, you can with Notepad++. Each antenna component has its own Fortran card, which you have to construct. So a wire has to be built. A transmitter, which is called an exciter, has to be built. Ground has to be built. The type of load, which we'll talk about in a second, has to be defined. Everything has to be defined in one single card, which is one line, ultimately, of code in this text file. We'll be using a text editor. Hopefully you guys will use Notepad++. Notepad is built into 4NEC2. But like I say, it leaves a lot to be desired. There's also some other editors which we're not going to cover. We're going to use direct writing of the cards because that ends up being the most powerful in the long run. Also, the original NEC2 punch card manual is available, and I'll show you how to access that really easily. Okay, the format is I'm going to set up some exercises. I'll prompt them, and then I already have them done. I have a file that works perfectly the way I want it to work. and I'm going to give you an outline of that file, and I will want you to populate the Fortran cards in a file of your own, and then run that text file with Fornect2. So you guys are going to be doing a lot of work. I'm going to be leveraging work I've already done, and hopefully this process will lead you to learn how to build a antenna model completely in a text file, which will enable you to migrate it to a symbolic format in a little bit, and also get you completely used to using Fornect2. After running the model, I would like to describe one of the things that I haven't been able to turn off in Fornect2, but Fornect2 does a great job of, if you have models that you already like and you run them in a directory called C:, for you guys using Windows, C:/Fornect2/out. After you run your first model, you'll see that there are some binary output files that capture all aspects of your recent run. Then when you close and go to dinner and come back and you open up Fornect2 again for that file, all of your results are still there. You don't have to rerun your model each time you launch. And that's a really convenient thing, unless you are making changes and rerunning and making changes. And then in order for your text file to be picked up by Fornect2, you have to run it 2 or 3 times, and sometimes it just won't pick up. And if you happen to make a dire mistake, like putting 2 transmitters in the same file, it'll write out a permanent file that has that mistake in it. And in the future, Fornect2 just won't run until you delete that file. So I recommend that once you guys get going, you open up a command prompt window and you go to the directory C:/Fornect2, write this command down right now and type it in at the command prompt after you run your first model and it runs through successfully. After you run your first model, you've looked at the results, you want to make more changes, run this command and blow this output file away so it's not hanging out there to prevent you from moving forward. Okay, any questions about this? Good. Okay, so we're going to start work. We're going to build a wire dipole. It's not going to initially be an inverted V, it's just going to be a flat top. And I want to remind everybody and those who haven't seen this, it's important. So the method of moments that NEC2 uses and the Fortran code, it'll run if you build an antenna like this, but it'll give you bad results because the solution can't handle, it can produce a result, but the result will be inaccurate if you have acute angles in your program anywhere. So as you grow in your capability and you build an octagonal antenna, remember that every time you turn a corner, you have to round that corner off with a small bit of wire, okay? So we will, let's see. Okay, so I blew through this slide on Wednesday and I want to take a little time to go through each one of these Fortran cards. So the wire Fortran card consists of a wire number, which is absolutely critical because if you put in a transmitter, you have to tell it which wire you want to transmit from. You have to specify a number of segments, and I'm not going to tell you guys how many segments to use, but for today's exercise, 20 to 50 will be fine. And it's very forgiving how many segments you use, and even better, if you use the wrong number of segments, when you run the model, it'll tell you. It'll say, you've got a segment error, and you can go back and figure it out. So you don't really have to spend a lot of time pre-calculating the segments like I did when I first got started. You just put them in. If the program runs, your segments are fine. They're okay length. Then, having put in the number of segments, you have to define in 3 dimensions. Today will be 2 only, but in general, you'll have to define your antenna in fully 3 dimensions and specify each wire end point. So you'll have to specify an XYZ for one side of the antenna, whatever wire you build. Let's say today we're going to build 3 wires, a left wire, a center wire, and a right wire for a flat top dipole. For each end of each wire, you have to specify a point that defines that wire, and each card then becomes 1 wire, okay? You'll have to specify a ground, and I'll go through what has to go here in ground type. There's always zeros here, and then dielectric constant, which I have for New York soil, and conductivity for New York soil, and I'll give that to you. A load can be many different things. It can be insulated wire, it can be wire characteristics. In this case, we're going to use copper wires. And in general, you have to assign, for many loads, you have to assign each wire. But for this particular load where you're doing copper wire for everything, which we're going to do today, you only have to use this card once, and it will use it for all your wires. But beware, because there are other loads that require you to assign a specific wire to it. We'll do a transmitter. That's called an EX or an exciter. You have to give it a type. We're going to use voltage. I have used both voltage and current, and I've never seen a difference between the two. Maybe there are some antennas where that matters, but I don't know where they would be. You have to give it a wire number. So which wire do you want your transmitter to appear at, and which segment within the wire do you have to place it? So up here, you're going to have a wire. You're going to give it 3 segments, for example. And down here, you're going to say, well, at wire number 3 in the center segment, which would be wire number 2, you're going to put your transmitter. And there's going to be a real and imaginary part that's going to be 0 today. Okay, and then I'll show you what goes here. Okay, so our antenna today will not, like I say, be an inverted V, but you can see this rounded off center wire better with an inverted V, so I left it. We're going to have 4 wires we're going to build today. We're going to have wire 1, which is the left leg of the dipole. Wire 3 is the right leg. And wire 2 is this little center part, which was where we're also going to place a transmitter. And we're also going to, because in field day and many applications, we put up metal masts. And depending on the angle of this particular antenna, that metal mast actually affects things. So we'll see that later on when we do it's not a strong effect for this antenna, but for some antennas, it's very strong. And it's good to have one more wire, a support mast. And we'll leave it copper instead of steel. Okay, so now hopefully you guys have a pencil and a paper and a calculator. So I don't know if you can see the very top of this screen. So we're going to start with the classic 468 divided by the frequency to come up with the overall length of the antenna. So we're going to do it for 20 megahertz, and we're going to do it for the bottom of the CW band, or the data band, and which will give us an antenna that's a little too long on purpose, because I want to show some things about that, and we're going to manually trim it. But start out by calculating the total length, and then in the middle, and convert that. This is going to end up being feet. Convert that to meters, and then let me just quickly check something. Then I want you to decide how long you want the center to be, And in mine, minus 0.1 meter plus 0.1 meter would be okay. I used minus 0.15 and plus 0.15, but decide how long you want the center to be. Subtract that out from the overall, divide the rest by 2, and you have all of your lengths, which you'll need. Calculate all your lengths. The antenna height is going to be 30 feet, which does not mean that you can put 30 into the length for this. You have to shorten it, and your XYZ values have to be slightly above ground, because if you touch ground with this, the NEC2 platform won't run, or it will run and give you a bad result. So when you build your little pole here, your support mast, keep it up off the ground a foot or half a meter or whatever you want, and then don't make it go all the way up to touch this wire, because touching wires in NEC2 is not allowed. So build this mast slightly off the ground and slightly below the antenna. And you can pick whatever you want to subtract to make that happen. Okay, so I would, if I were you guys, draw this on a piece of paper, calculate the length, draw out the height, and then I would label every single, on that piece of paper, I would label XYZ here, the actual numbers, XYZ here, the actual numbers. And remember, we're doing X and Z only. So we have plus Z above here, here's 0. And we have minus X and plus X around 0. Y is always 0. Okay, so this antenna, all of the wire cards will be Y always equals 0. All right. Any questions about what we're going to do? Okay, so I'm going to give you guys a template. So this is a template for your entire model, which you can use and modify. So this template requires actually that you only specify X1, Y1, and Z1 for the left leg, X2, Y2, Z2 for the left leg, and then specify the same dimensions for the center, the same dimensions for the right leg, and some dimensions and some for the vertical support. So if you guys take a few minutes to work out all of these different coordinates, as you move to more complicated antennas, this will be a very time-consuming aspect of building the antenna. Everything else is usually some cut and paste. And then as you finish, just raise your hand so that Carl can see where you're at. And at some point, he'll let me know. If you if you get stuck, if you can't figure out the dimensions, then we can go back and we can work on that. But for example, 468 divided by 14 is around 30 feet. Convert it to meters. Divide that, well, subtract out 0.25 or 0.3 meters for the center. And then for the other length, specify XYZ and XYZ1. Remember, X1, let me show you, it's a negative number because it's minus X. And the total distance minus for whatever you have, minus whatever this is, has to equal half of the antenna. So let me know when you guys are. I'm going to leave this up so you can copy it, and then I'm going to flip to the template. And fill out, for me, filling out all the dimensions on the actual antenna first greatly aids filling out the dimensions in the card. Because you know which card, you know which dimensions go with which card. Okay, assuming you guys have this little picture written down and the coordinates sort of, you know what you're doing with those, I'm gonna switch to this template. So you can, once you have your antenna all filled out, you can then fill this template out in Notepad++, hopefully, or Notepad, and save it to a directory.
Yen, do you have a question? Or are you done?
Oh, yeah, I have a question. I
Okay.
guess this is the first time I'm using the 4NEC2, and I'm wondering about the segments. There's X, Y, and Z, and then there's like a space in between, and they're not antenna segments, and the ground is not supposed to touch. So how much space am I supposed to leave?
You're talking about the vertical support mast. Which part of the antenna?
The orange dot.
Okay, so the center. So in the case of this, when you put it all together, they're all going to be lined up exactly. Let me show you. So here I have minus 5.223. That's the length that will be appended to minus 0.15. So they're stacked right on top of each other. And this is the left leg of my antenna. So you can, for the total length in here, which you then divide by 2, one for the right leg and one for the left leg, you can pick anything less than 0.1, 0.3 meters, basically. Does that help? So, in this drawing, Yen, I have shown a gap here to make it clear there are 3 segments. The antenna actually does not actually have these gaps.
Right.
So the horizontal wires are actually touching. It's just the mast, that vertical wire, that's not supposed to touch the horizontal wires.
So XYZ1, where it touches the orange, equals XYZ3. So the left leg and the right leg by the orange dot are actually the same point in space?
Correct.
Oh, okay. Thank you. But what about the bottom dot? XYZ2, is that the same dot as XYZ1 and 3?
XYZ2 will be the same as XYZ1. And then this XYZ2, so I did a bad job here of labeling these. This XYZ2 that you see on the screen will be the same as this one, correct?
But XYZ1 and XYZ3 are the same points.
No, XYZ3 is going to be plus point whatever. XYZ1 is going to be minus point whatever in X. Let me show you.
And they had to be 0.3 meters apart?
So take a look at this model, Yan, real quick. It'll help you. So for my left wire, which is shown right here at the top, I have X1, Y1, Z1, X2, Y2, Z2. Now, X2 here is the right side of the left flat part of the antenna. Then immediately next to it is the little center part. And it starts at the same place this guy leaves off. And it goes a short distance to plus 0.15. So we cross over 0. And then the right side takes up where the right side of that little center part is and keeps going to the right, the exact same amount that we do on the left. Does that help? So this top guy right here is the left guy right here. And then the, wire 2 is right here, and it's the center. And you can see that its total distance is 0.15 plus 0.15, or 0.3 in my case. You can make it 0.2 or 0.25 or anything you want. I mean, that's not too small. And it has to have an odd number of segments, because you're going to put an exciter right in the middle. So you need an odd number. Okay. And then here's this third wire is the far right of the antenna. And it starts at the place where the center point, where the center wire stopped on the right. So the left part of the right wire starts at that point, and it extends the same distance that your left leg's extended, same magnitude. Good question.
Would you be able to put the GW3 at negative 0.15?
You would be able to, and however, your antenna would then have 2 left legs, or if you if you make this minus 5.223, you'll have 2 identical wires, and I really can't say what it's going to look like. But you have, in order for you to use this coordinate system, minus x and plus x, which Fornec 2 expects, with 0 right here. So the coordinate system 0 is at the bottom of the mast. I mean, it's actually at the ground. The bottom of the mast has to be slightly above ground. So we have XYZ equals 0 right at ground here. And all of these points are relative to XYZ 0. So the X point has to be minus for a dipole. And on this side, all of them have to be positive.
Okay. I would have thought that the G3 would have started at negative 0.15, because that's like the center.
No, that's another good question, but look at GW2. It starts at minus 0.15 and it extends to plus 0.15 right here.
Okay. Okay.
And so it takes up all of the space in the center of the antenna on the minus and the plus side. So then the right side has to start where the center wire ended. Do you see?
Oh, got it. G4 is the
Fantastic.
one that's the mast. Got it. Okay, thank you.
No,
Got it.
I'm glad you got it, and I'm sorry that this isn't more clear. I tried to draw it as clear as I could without, but ask any question, Yen. Your questions were all really good. If anybody has any questions, please don't hesitate. The first time I did a exercise like this, it probably took me 2 hours. So, but I'm much older than some of you guys. So let me know if I'm on the right picture or diagram. We're filling this guy in. If you need to look back at this for some reason, let me know. Or we're filling in this template.
Do we assume that everything past the pound sign is a comment?
Everything past the pound sign is, oh, good question. So when I blew through this, I didn't explain something that's important. You mean this pound sign here, is that correct?
Right.
Very good question. The answer is no. There are two ways to make a comment in Notepad that Fornec2 will interpret as comments. One is to preface it with a CM, which I have done here. And I always do when I'm here in the code because it's sort of similar to writing code. However, if you want to denote a line of code, there's another way of adding a comment at the end that will be interpreted as a comment, and that is with this little bitty tick mark in front of the text. So what is the pound? The pound defines, in my case, I built all of my antennas with 14 gauge THHN copper wire from Home Depot. So Fornec2 allows you to specify, this is actually the radius location of the wire. So every wire card has to have a radius of the wire. You can define the radius in millimeters like I have done here, and you can define the gauge of the wire, and Fornec2 will do the rest of the work. So to define a radius in this location, which is what I'm doing, you can do it in many ways. I have another model we're going to work with where I calculate the radius because there's no matching gauge of wire. But this is simple and helps me remember that I used 14 THHN for mine. So the comments, to summarize, are a little tick mark in front of text or whatever, and that can go anywhere. And also CM put in front of anything. I typically put in the wire definition. I typically put to the left because it's simply a paradigm I'm used to. Did that answer your question?
Yes, very much. Thank you.
You bet. Good question. Thank you.
And Mike, I have a quick question. This is Sam. The white spaces in the between the fields, or is it important for those to be a space, or can they be tabs, or is there a certain
Good.
restriction there?
A good question. So in Fortran, these areas between the entries are very highly specified number of, you know, little steps.
So
In
spaces.
the notepad,
Yeah.
you can make it anything from 1 space to 2 spaces or 4 spaces. You can make some of them 2 and then some of them 4. You can see here, I haven't actually done it very well, as long as there's a space.
So a tab character would create a problem?
So I do not know the answer, because in all of my programs, I've only ever used spaces on the assumption that the tab would not be recognized. So I
Gotcha.
cannot
Yep.
answer.
Okay. Space it is.
No problem.
Thank you.
I don't recommend using a tab anyway, but you could try it. If you're working in Notepad, it'll probably be okay. I mean, Notepad++, I'm sorry.
What is the third item on each line?
In the wire card,
Yes,
1, 2, 3.
yes.
This guy? Good question. That's the number of segments. And if everybody will take a break for 1 second and look up, I want to show you how you answer your own question in that regard. Let me show you the first and most effective way to answer your question. But sometimes it doesn't cover everything you need. So if you launch Fornec 2, hopefully, if everybody take just a second and look up here, please. All right, so if you open Fornec 2, over to the right, you'll see help. You can access the NEC user's manual, which I don't recommend. And then Ari Voers made a NEC short reference, okay? So now here are the most common cards in the NEC 2 engine. And at the very top is the wire card, and you can see you need the wire number, you need the tag number, which is the first field right next to the definition. And then you need the number of segments, X1, Y1, Z1, X2, Y2, Z2, and you need the wire radius. So if you're working on a card and you forget or don't know what field is what, which happens to me all the time, I come here first. Now, if I'm working on a more complicated wire that's not listed here, then I go to Google and I'll show you a trick, and it's really amazing because this stuff is still out there. You type in wire card in Fornec 2. And the very first return for always these kind of queries is the actual NEC 2 specification website for that particular card. So somebody really did a lot of work to get this so it's really easy to sort out. And so you can read, you can take as much time as you want to read as much as you want about the card itself. So for example, if you wanted to put a load, you put load card in neck 2.
Open, it's on.
I know, I hit print.
So you can see all these cards just by typing them in at Google. But the first place I go, because it's actually more clear, is the help file and then the next short reference. And it's good to get used to using these because you will be using them many times. Now, what did I do with my display? Ah, there we go.
You got it.
Did that answer your question?
Yes, very much.
Okay, great.
So while everybody else is working, I have a quick question, Mike. I put in 10 millimeters for the vertical support diameter. And when I tried to run this, Forneck 2 actually interpreted that as 10 meters.
10
Did I do
meters.
something wrong? Did I?
You put
Rough.
10 mm here?
Yes, that's what I tried. And it came out as 10. So I don't know whether I screwed up and only had 1 M in there, because when I saved my file, of course, it overrode it. I made some
1
changes.
second. Let me, so I have exactly, I believe I have exactly that in my file. Whoops. All right. So what do I have? Yeah, I have 10 me,
Okay,
but I don't.
let me try this again. My problem is I'm juggling too many windows here. I have 3 Zoom windows open with the chat and everybody's picture, and then your presentation, and then in addition to that, I'm running Forneck 2. So my screen is a little bit crowded here.
It's, well, I appreciate your hosting and all of the, while also doing the class. If
Okay.
it's 10 meters here, I don't see it.
Okay, I'm now running it again. I'm doing it.
Did it come
From
out
scratch.
as a big pole?
I got a warning about the wire diameter being more than a third of the wire length or something like that.
So if you don't put the millimeter right next to the 10, you might get 10 meter, yeah.
Okay, maybe that was my mistake.
Yeah, there's no space.
Yeah, this time it took it. So I must have done something wrong.
Well, this is, I just want to say how many hundreds of times I have done some little thing like that and then spent hours to figure out what it was. So. So this process, just while everybody's work, well, I'll stay silent so people can focus.
Perhaps you can maximize that slide.
Oh, you need it bigger? One sec, I can make it even bigger, I think. So slideshow. Hopefully that helps.
Mike, you said something about the center leg had to have an odd number of segments in it.
I have 3, yes.
Is that so the excitement can tap
So
in
the
there someplace?
reason
Is
you
that why
want
it's odd?
The reason you want 3, the reason you want it to be an odd number is you're going to put the transmitter dead center in the antenna. And the only way to get it to be perfectly dead center is to have an odd number of segments defining that wire and then place it in the center segment of the odd number.
Okay.
Otherwise, your transmitter will be slightly off from center and it'll show up in the pattern that's generated. And once you guys do this a few times, you can play around with where you put the transmitter to see how, the impedance changes and the far field changes. It's kind of interesting. And you can see, well, for example, if you move the transmitter all the way to the left of the antenna so it's in-fed, you'll see how high the impedance is and how much of a matching section you have to build to actually be able to get it to transmit. So another reason it's dead center is that's the closest you can get to 50 ohms impedance for this antenna.
I assume we are starting to count the segments with number 1 and not 0.
Yes. So 3 segments will be 3.
And the first segment will be segment number 1.
That's
The
correct.
one in the middle will be number 2.
That's
Because
correct.
when you have a computer science background, you start to count with 0.
Unless you've been using MATLAB, right?
Haven't done that in a long time.
Well, it has an indexing that starts at 1.
Okay.
But Python and C and C++, all 0. That's correct. But you can think of this, Carl, as this is a real wire. So the first one is actually number 1.
Does it make a difference on the ground, or I mean on the pole, whether you start from the top and work to the bottom, or you start at the bottom and work to the top?
So I don't know the answer, but my X1, Y1, Z1 is the lowest. I always make X1, Y1, Z1 lowest. However, I suspect that it wouldn't matter.
Okay.
Looks like Duncan has a hand raised.
Yes, on the pole, on the vertical piece, what is the starting point? Is that 0, 0, you show 0, 0, 0, and I thought you said that the start of the mast had to be above ground. Is 0, 0, 0 the origin ground?
So hang on. GW4. So that's interesting. So since this doesn't have a transmitter on it, it probably didn't give an error. But in general, for the NEC 2 antenna system, connecting ground with parts of the antenna, which this is actually, it ends up being part of it in the reflected sense, is not a good thing. But clearly, I didn't get an error this time, and good observation, because always in the past, I have the pole slightly above. So the XYZ would be slightly above here. And I also don't know if this is the one that I'm actually using. Let me just check. This is PowerPoint. So let me just make sure I didn't do something that I'm not using. Yeah, it's working. So if you want to make it 0, 0, I recommend you do it and then change it and see if you get a different result. For this orthogonal antenna system, I doubt you will.
Okay, but in general, what you said originally was that you do want to keep everything off the ground.
So yeah, stuff that's gonna, like, for example, if you build a vertical, you can't put wires in the ground. It'll return, along 0, it'll return a result, but it'll be nonsensical. And for now, NEC 4, which requires a paid license from Lawrence Livermore, NEC 4 compiled for Windows does use, you can do buried radials, your mast can be stuck in the ground, and then all of that will be accurate. But I'm going to change this program to be 0.1 off the ground because I know for a fact that NEC 2 can't handle metal sticking in the ground.
Okay, thank you.
Yeah, my apology, guys. I still make mistakes, and hopefully you won't find too many of them. But that's a good point. It will run, and that might be why. Well, I'll do a little research and see if I get a different result. But for an orthogonal system like this, I don't think I will.
Mike?
Because the mast does not interact really with the antenna for this flat top.
Was there a question?
Yeah, Mike, this is Jack. The directory that we save the model from, Notepad++, do we save it in the fornec2/models/file name?
You can save it. So let me show you where I save my models for this class. So all the models that I have are on my D drive under fornec2 antenna modeling class. And you can save it to any directory you want that subsequently you can find again. And then when you want to run it, you just double click it and fornec2 will launch.
Okay.
Assuming that you have it .nec as the end.
And what if you go to fornec2 and do the file open procedure?
You can do that too. So sometimes some of my models are written in .txt. There might even be some here because I did all of the editing in Notepad++. Here I did .NET. This is .NET because at some point I used the fornec2 Notepad, which saves out as a .NET file. So, you guys, if you're working in Notepad, it's going to save it out as a .txt. And if you double click that, fornec2 will not automatically recognize it. But if you change the end to .nec, or if you just file open and reach it with a .txt, it'll load just fine. Good question.
And it looks like Joe has a question.
Yeah, Mike, thanks. This is great class. Question again on the length of wire 1 and wire 3. Did you say you do subtract off the point or half the 0.3 on the length of each of those, or how do you calculate that?
So here it's not complicated. So you add minus, it's more, by that I mean it's more complicated when we get to variables, as you'll see. But it's not complicated here because this number plus this number, well, let's use positive. So this number plus this number have to add up to half the antenna. And then if you start with a negative number and you subtract this, then that has to be half the antenna as well.
Okay, I'm not. I guess the question is a center, if you figure out the quarter dipole length, not including the center, is the difference between that the real quarter dipole, or do you have to consider half the center part of the dipole as well, quarter dipole?
Good question. So when you use 468 divided by 14, that's the total length of the antenna.
So that's a half wavelength.
Half wavelength, correct, but that's the total length of the antenna we're going to use. So these three, GW1, GW2, and GW3, the sum of their total length, I mean the distance between X1, Y1, Z1, and X, has to, all three of these have to add up to 468 divided by 14 and then converted to meters.
Got it. Thank you.
Good question. Yen, how's it going?
It's
no.
going well. I guess it's because I'm Canadian that converting to feet and metric is, I'm using a Google calculator to do that. I think there might be some differences if I just used metric all the way through. I have simulated something, so I guess it's okay.
Well, we'll go through the simulation when everyone's done, but you have all of your units uniformly in meters,
Yes.
then you should be okay. And yeah, it's a pain to do this correction, and then I'm going to show you in just a minute a way around that, and then hopefully you won't be too aggravated I didn't show you up front. So it's possible to actually program in feet. And that conversion factor you can put in the program, but this one time I wanted people to program in meters because the program will run faster if you program it natively in meters.
Oh, I think natively in meters.
But
That's
this little equation, this equation we started with is in feet.
but that only gives you that's lambda by 2, right?
Well, this gives you the total length of the antenna that you want. And then if you're building the antenna, you divide it by 2 and put the feed point in the middle, which is what we've kind of done here.
I clarify for her.
Sure.
Yes, Yin, the equation gives you lambda over 2, as you said, but then you divide it again by 2 to get each end of the half wave dipole segment.
Got it.
Correct. Well, to get you get the total length of the antenna. And if you were going to build the antenna, you would divide by 2. Here, you have to break it up into 3 segments. So you can divide by 2 to get a rough approximation of the longest segments, but you have to subtract off this bit of space you have for the center part. So that in the end, wire 1 plus wire 2 plus wire 3 adds up to the number you got from this calculation in meters.
I guess my lambda over 4 for like one whole arm plus a little space would be 5.3575. And I noticed in your example, like the left leg plus the little part of GW2 would be 5.223. So
Very good.
there's like 10 centimeters off. Why is that?
10 centimeters off from what, Yin? I didn't follow that.
Oh, so when I calculated lambda by 4, it's for let's say GW1 plus half of GW2, it's supposed to be 5.3575. But I noticed your GW1 plus half of GW2 is 5.223.
So my GW1 is 5.223 for the left X. And
Right.
then for the right X, it's minus 0.15.
Mm-hmm.
So I take and I add 5.223 plus 5.15, and that's the length, correct?
No,
No,
No. I add
No.
those two. I add those
no,
two.
no.
you don't do
Uh,
anything with that. Your antenna goes from minus 5.223 to plus 5.223.
Oh, the whole antenna, yes.
Yes, so that should be your lambda half.
yeah.
So there's
Oh,
no
okay.
correction that we have to make. It's just from the leftmost point to the rightmost point. That's our half-wave dipole.
Correct. And if you just forget all the signs and you add 5.223 plus 0.15 plus 0.15 plus 5.223, that works out to be the total length. Now, I was confusing
No.
you because the sum of this in negative is equal to the sum of this in positive if you ignore the negative.
The 5.223 plus and minus are the endpoints in the X dimension, not the lengths of those segments.
Correct.
So the length is twice 5.223 meters.
So the length is 2 times 5.223 plus
Correct. No,
plus
No, there's no
no.
plus.
Right?
oh,
The length of
yeah.
segment one is
No.
5.223 minus 0.15.
Yes, okay.
So we're subtracting out the 0.15 to get the length of that segment one. And then we're adding it back in when we look at wire 3. But the length of the overall antenna is twice 5.223.
That's correct. Yes.
I guess when I calculated out for lambda by 2 in metric, I get 10.715 meters. But for your example, it's 10.446. So it's a little
Right.
shorter.
Right. And the reason for that is I tuned, so I did not use 468 divided by 14 to build this particular antenna. And I have already tuned this antenna. So this is an example. I've tuned this antenna to be a specific minimum SWR at a specific frequency. And I will eventually ask you guys to do the same thing.
Oh, okay, got it.
So sorry for not being clear that this isn't exactly the same model you have. You have a different starting spot.
Makes sense. Thank you.
So if this number is different for you, it should be. And in my mind in teaching this class, I was not going to actually show this until you guys were a little farther along. I was just going to show this, but this helps to define these numbers. Good questions, Ian. Thank you.
Like, question on the exciter specification.
Yes.
In column 5, you have a 0. What does column 5 represent?
Good. So I'm going to go through all of these when everybody's are done, but this, let me just do EX right now. 0 is the type of transmitter, meaning it's a voltage if you look it up. This is the starting wire. Number 2 is the starting wire. This 2 is the starting segment of wire 2. This is, what is this? 0, 1, 0. Oh, so let me just think here for 1 second. All right, so
I looked at the cheat sheet and it's not clear from that.
yeah, well, hang on. This is what I do. Hang on. Maybe okay. So EX card. Can you guys see this? Let me try to blow this up. So I recommend you guys do the same thing I just did. Open up Fortnite 2, go to help, and look for the next short reference. And you'll see EX card right here. So 0 voltage. So voltage source is this first field, which yeah. So this ends up being 0. Then the second field is the tag number, like I said. Third field is a segment number. And then I think these XXs, real volts and imaginary volts. Correct. So this is what I'm not sure what XX is, but it's real volts and imaginary volts. So now let's go back. With that in mind,
if you were to look at the right-hand side of that line, the XX is explained, I think, I could be wrong. It's a 19 or a 20, something like that.
so hang on.
It looks
an
like
EX
it's a
card.
0, it's no action.
This is voltage type. This is the wire and the segment where the transmitter is going to go. This is real and imaginary. And
Oh, you skipped. That first zero
wait,
is
this
not
is
real.
probably real and imaginary. Let me go back.
Yes,
Right.
yes, that's correct.
it's
So this
column
is real
5.
and imaginary, and I just have to sort out what this 0 is.
It sounds like no action when we look at that legend to the right.
Yeah, I don't know what this, so 0, tag number, segment number, then I have a 0, then I have 1 and 0. So I don't know, guys, what that 0 is.
We know 0 works.
I know 0, I know 0 works. That's correct. And you guys are going to run up against all my limitations, I see, which is good because I get to learn too. And it's hard to hold, even if you do this like every day for a month, it's hard to hold all these cards in your head. At least for my 62-year-old self.
So Mike, it's Peter, I noticed that you used the help file on the NEC executive. When I hit the help, I get an error. Must I load additional help information into a folder?
So let's just follow me here exactly and let's see what happens. So I know exactly what you have done. And so I'm going to close this. Do you have an icon on your desktop? Peter, you're on mute, sorry. Uh-oh.
Okay, let me reduce the full screen so I can get to the. Yeah, I open NEC And I
So
go,
but do you have an icon on your desktop?
yes.
All right, I'm gonna double click mine. What did you do?
Well, I double click mine and it
Okay.
opens up V 9.5.9.3. And I see all the, the information that you have.
Yeah,
But if I go to the main executive there's a help on the far right side.
are you look up at my screen, Peter, for 1 second? So I'm showing that along with the next short reference.
That's right.
You see that?
You've hit help.
Yeah.
Okay, short reference.
I move my mouse, I hit help and I move my mouse down until it lights up, next short reference.
Yeah.
I click it and a Word file comes up.
Well, I get Microsoft Office Word gives me an error. Command cannot be performed because the dialog box is open. Oh.
You may have some Word dialog box open in a different document.
Okay. I understand. I hit it again. I get the help file. So it is working for me. Thanks.
No problem. Thanks for the question, Peter.
So John put a comment into the chat about the zero, the mysterious zero. And I actually looked it up and there's some explanation online about where is it? Columns 19 and 20 of this field are used separately. The option for column 19 are: one is maximum relative admittance matrix asymmetric for source segment and network connection will be calculated and printed. So it's the long version of what we found on that help document. And zero means no action, which is what we are using.
Very good. Thank you, Hans. I mean, Carl, what am I talking about?
I'm Hans.
Yeah, I was looking at the right and I was reading Hans but it was Carl that was talking. Thank you. So this is related to how the exciter is constructed. So how are you guys doing?
Peter, are you trying to talk? You're muted, but your square is lit up green, so it looks like you are talking.
Yeah, let's go on.
Well, the next part of the go on is where we run the model. So if you have a model, we can go on. If everybody has a model, but if people are still generating their model, then we can't quite go on because the next phase is for you to begin the process of teaching yourself. And I'm going to show you what you can do while you do the same thing.
Oh, I thought you were going to explain all these other lines like the ground type and exciter type and things like that.
Oh, okay, we can do that. Well, you guys already know about the comment. By go on, you didn't mean move on to the next phase of the class. Okay. So comments, you know, the wire you're learning real time. The most important, well, you have to get the dimensions correct, and you have to get the segments correct, and the wire numbers correct, and in sequence. You always have to specify a radius, and there's multiple ways to do that. And it's hard to figure it out how many different ways there are, but these two have worked for me. And then the GS card is a card that I usually don't use. So, but today I put it in so you guys know it exists, so that you can, if you want, program in feet, in which case you would put, instead of 1.0 here, so all of this antenna is in meters. So the scaling, this is called a scaling card. And since everything is in meters, the scaling will be 1.0. And during the model run, all of the antenna links will be multiplied by 1.0. Now, in this case, that's pointless, but I put it in so you guys can see. If you program in feet, so that all of these lengths are feet, you change this to 0.3048. The 1 becomes 0.3048. And assuming you put this card in at exactly this location at the end of the wires, it'll run correctly. Now, if you run Fornec 2 once, it really doesn't matter whether you have a GS scaling card in there or not, because it runs pretty quick. However, when you start doing frequency sweeps across an entire band or multiple bands, let's say you build an OCF and you're going to scan from 2.6 megahertz all the way up to 30 megahertz, then you're going to run 256 different slices with Fornec 2, and this additional little bit of mathematics takes a lot of extra time. So generally speaking, I program only in meters, and then I don't include this scaling factor because it's not needed. And when I do a frequency sweep across an entire, multi-band antenna, I don't have to wait for, 5 minutes for it to run. All right, now this card is very important. This is the end of the wires, GE, end card. And when you set it to 1, that tells NEC 2 that you're done specifying the wire dimensions, and the next is going to be something else. Okay. The GS card has to be inside the GE card. I'll double check that, but I think it has to be inside. This is the ground card. Okay. This particular card, if you go read about it, is a Summerfield ground. There's a bunch of different ones, including free space, and they all look different. And this is the dielectric constant, and this is the conductivity, and I think this is the dielectric constant in Siemens, I believe, or something like that. Anyway, you can look it up, and 0.005 is the conductivity, maybe in moles per meter, I don't recall. This one for sure is moles per meter. Okay, so this is the ground card, and this dielectric constant and conductivity are consistent with northeastern soils. Now, interestingly enough, I had another guy who has a dielectric constant meter measure it for snow, and it's totally different. So if you have snow and you want to see how the antenna behaves over snow, I can send you a different set of these numbers, and it'll change everything profoundly. So if you've ever gotten a lot of snow and you saw big differences in your antenna, that's one reason why. Okay, the load in this case is one card. You don't have to do it for each wire. It will assume that all wires have this if there's just one entry. and it will apply this conductivity of wire to all of the wires. And this is for copper. So it's 5.8 times 10 to the 7th. A good number to remember. We went through the exciter. And then the second to the last card is the frequency. And let's see. Obviously, that is the actual frequency that this particular model used. We're gonna do something different when you guys, and now we're gonna have to look up 0100. So the gentleman who asked the question, if you would look these up in the help file and tell us what it is, that would be great. Is that okay? Hang on. Let me look them up. All right, back to the model.
Does that load card, you haven't commented their wire type. Does that have to go inside the wire definition area?
Hang on. I'm just looking up frequency real quick. The frequency card. Oh, yes. All right. So the frequency card really for if you just have one frequency that you're going to use, and you're going to use the 4NEC2 built-in capability to scan frequencies, you don't need this. You don't need to even know anything other than the structure that I've provided, which is basically you can define whatever frequency you want and keep all this other stuff the same. Okay. Now, if you want to scan across many frequencies and generate a bunch of different files, you can set up the frequency card with a number of steps, the start step, the step size. Okay. So, and I actually 0 is just defined here, like, okay, it's got to always be 0. I don't know why. Same here. So that's where those zeros come from. And I haven't included any of the steps because we're just going to use one of the, we're just going to use one frequency.
That first 0 looks like it's linear versus log.
Yep, that's so in the help file it says you can step linearly or step with a log if you're really going to go across a lot of frequencies or a wide range of frequencies. For HF, I mean, you don't have to sweat it too much because you're not going to step typically from HF all the way to, well, I've stepped all the way up to 50 megahertz with linear. From 2.6 megahertz to 50 megahertz. And then the end, EN is the last, tells the program that there are no more cards.
So if you want to do a SWR sweep across frequencies, is this the parameter that you would adjust to enable that?
No, I'm going to show you how to do that. 4NEC2 has that capability built in. And once we get our antennas built, we're going to take a look at several things. And one of the things will be a frequency sweep, Peter.
That's great. That's powerful.
And again, the frequency sweep, the rate at which you can generate it is somewhat dependent on, like if you just have to program in feet, that's how you think, and you put in with 0.3048, and sometimes it does help since we all grew up doing feet. If you're not going to scan a huge range, if you're just going to go from 14 to 14.5 megahertz, you can use feet and you can use this scaling factor. But for example, I have an OCF that is all band except for 30 megahertz resonant from 3 megahertz to 50 megahertz to 55 megahertz actually. And so when I scan my model for that, I run a full 256 or 255 scan, and it takes a while. Especially if I put in the scaling card so that every wire has an extra multiplication. So in a couple minutes, how's everybody doing? Are you guys getting close to being done, or we're still working?
So I got the data on paper. We have to make an entry into a file now.
Yes, Peter. So if you have Notepad++, so I'll show you. Do you have Notepad++, Peter?
I downloaded it and I couldn't find it. So no, I don't have it right now.
Okay, no problem. Let me show you something. Are you watching my screen?
Yeah.
Okay, so if you open up Fornec 2 and you click edit, first go to settings and select Notepad edit. Now go to edit input. And you'll see a blank little thing come up. It'll just be a blank whatever like this. And you can type in all your stuff from here. And then you can file save it when you're done. Okay. So Fornec 2 has a bunch of editors built in. It has Notepad, not Notepad++. But if you don't have anything, Notepad's better than nothing. Do you see it, Peter?
Yeah, I understand. So it sounds like it's a lot easier to use Notepad++. I gotta find that and download it again.
It's only a minute or so to download it, go to the directory and install it, and then you can use it. How about everybody else? How we doing?
We get one thumbs up from Rich.
File created, saved, ready to run.
Very good. Yin, how are you doing?
Okay.
I'm good.
We got a whole bunch of thumbs up.
Done. Good.
It's an optimistic thumbs up.
Okay. Well, because we're running out of time, if you guys will suspend what you're doing, what I want to do is show you how to analyze, and then I don't want to save that. Oh, me, yeah, I do. Okay. So now I'm going to go to my directory where I have saved all this stuff. I'm going to go to Fornec 2 where I have saved, and it can be any directory, antenna modeling. And this is what we've been doing. Okay. So if you guys would just take a look up at the screen, please, I'll show you some cool stuff about how you can analyze this antenna. So first of all, when you open the antenna, there's a beautiful 3D view of the antenna, which you can see, and you can see if you made a mistake in the geometry. You can see if you've got the transmitter appropriately located. Can you guys all see this?
Yes.
Okay, very good. So This will be the pane where you will get some results, and then there will be other panes where you can get many more results. So I'm going to just press F7. So you might want to remember F7. F7 brings up, without having to click and use your mouse, the run. So you can run this file. If you just press the down arrow key, you can select far field pattern. I've already programmed 14.0 megahertz. So I'm going to generate a far field pattern for 14 megahertz. So here we go. Okay, so the first thing that comes up is this. I have phi equal 90. Down here, if you see this, I have my system, and yours will default to phi. What this means is I'm looking at the antenna from the side. So I'm looking at the antenna as if I'm looking down one end, okay? And which is, let me show you what this slice shows. So if I look at the antenna, and I'll show you this in a second in more detail, but if I rotate the antenna and look straight down the antenna like that, then the pattern looks like this around it, okay? Now, I can prove that by show far field pattern. Okay, so now this is an incredibly useful view, and I'll go back and show something. So I have selected to build slices every 2.5 degrees in a 360 degree wraparound angle for the antenna. So when I rotate up now, I can see relative to the antenna, the pattern. And I have total gain and dBi here. I don't remember what it actually comes up as default, but you can change it by selecting far field and check whatever you want. ARRL style, blah, blah, blah. So there's a whole host of stuff. Now, this is really powerful as well. So I now have generated this far field pattern. I rotated it so that the antenna is XY in the XY plane, and I'm looking down on it. So if I come back over here and click in this screen, the first thing I can do is press I. So if you guys are taking notes, it's hard to figure out all these little shortcuts over time. So if I press I, Fornec 2 will go and locate the exact angle, which is the maximum gain, which is useful if you have more complicated system or even if not. And then if I come here and I click right there on that blue line, I generate, or if I click here, I generate, hopefully you can see, I generate the gain and the angle. So I can deduce all the way around this, straight up, what's the gain, all the angles for this one 90-degree slice, okay? If I would like to know the more details around the antenna in terms of numerics, I stay here in this screen, click the angle I want to see more detail about, and then go down to the keyboard and press the right arrow key near the numeric pad. So now you can see I'm rotating through each slice, and each slice shows up in high detail on the left. And if I have pressed I can continue to track the angle evolution for the largest gain, okay? So if you're doing some quantitative work, you can pick off a few and make some plots, that kind of thing. And you can rotate around the entire antenna as many times as you want. Well, then you can rotate all the way back. Okay, so this is an incredibly useful capability that is really unmatched. EasyNet is a good platform. I have it installed right next to Forneck 2. But it just doesn't have anything like this kind of graphic. All right. So that is a quick look at what you have in the default screens. Both of these screens come up, and all you have to do is say show near far field. There's a bunch of other stuff. There's something else you can look at that's very useful. So let me get rid of let me leave it. So
now, before you, Mike,
yes.
Quick question. I'm trying to follow along here.
Okay.
But somewhere I must have done something wrong because my pattern disappeared and I had to figure out how to get it back. How did you walk through the different slices?
Okay. That's no problem. I think that's one of the coolest and most useful things about Forneck 2. And if you're working on some high detail with a complicated antenna. So the first thing you do is come over here to this screen, sorry, and show the far field pattern.
Yeah. And is there a shortcut key so that I look down on it, or do I have to manually rotate it so that it looks like that?
As far as I know, I've always rotated it. I haven't been able to find a key. There may very well be one, probably is, but I don't know what it is. So I rotate it and line it up. Let me just try a few obvious. I've tried this before, Carl, but so I'll see if I can find one, but so far I rotate it. It's not too bad. So now once you have this view, however you get it, let's say I have to rotate it, then you move the mouse, then you take the mouse and click in the square that has the far field pattern.
Okay.
And if you want to track a specific angle, you click, for example, 65 degrees, which is, let's do a 10 degree launch angle, or 5 degree. Let's see, 70, 90, 75. Let's do a low launch angle here, 75, because low launch angles mean you can do DX. All right, now we want to see how that gain changes at that angle as we go around the antenna. So now your focus of your mouse is on the left, but if you go to your keyboard, you should have an up arrow, a down arrow, a left arrow, and a right arrow. For the moment, press the right arrow.
Okay, now I see it change. Yeah.
You can see it?
Yes.
Outstanding. All right, this is good. I did some work with comparisons between the hex beam and this spider beam, and this was extraordinarily useful because we're trying to do field day with it, so we have to cover a wide angle. And it wasn't so much the max gain we were hunting, it was more the broadband nature in terms of the angle. So so we could cover, the whole United States without having to manually move the thing during field day. All right, now this gives you a lot of information, especially if you're looking at very high detail. However, there's this really cool view over here. So if you see this little 3D viewer, so I move my mouse over to this pane, I hover over this little bitty 3D icon, and up pops 3D viewer, and I press it one time. Okay. Now I have another way of 3D viewing this antenna in a kind of a cool, there's ground, it's green, sky's blue. Oh, you know what? I don't want to go here just yet. There's one more thing I want to show over here. Sorry, guys. I don't have a slide set for this, so let me get it mostly horizontal again. Okay, so currents. So if you're building an antenna where you have interactions between the elements, like a beam, or we're gonna, even with this, once we convert this into a model, even in inverted V, you're gonna wanna take a look at it because there's a puzzling result we're gonna have. But you can click right there and you can set the color, whatever you want. This is the current amplitude, okay? And it gives you a good clear view of the currents along the antenna, showing that at the feed point, the current is largest. And if you're interested in the phase, you can see the phase visually. So if you're trying to build an antenna where two elements maximize their phasing to get a maximum current gain out there, you can. And then current and phase. All right. And then the real component of the current, which is the default view. And then the imaginary component, which is zip. So that gives you a lot of information. There's many other things you can take a look at. You can change all kinds of stuff in here. These three, show far field and the current density, those are the most useful. Okay, now having introduced current density and far field, let's go back over here and figure out how to see the same stuff here. So structure, let's select current. Okay, so now I can see the current. And then I see I've hidden the pattern by default, so I want to go to multicolor. Now, I don't know how long it took him to write this. He used a graphics package. There's absolutely nothing that's this cool in EasyNet, not even close. And even before I had a very powerful computer, these graphics, they functioned really rapidly and smoothly. Now for this antenna, this view is more like, wow, that's cool. Let me show my little sister. But if you have more complicated, like if you have an off-center fed dipole, it's sometimes hard to see this detailed, you know, it's hard to get a good global view of how an OCF radiates for 20 meters on a 80 meter OCF because the lobes are so complicated. And I will show that if we have time in this class. But this, for complicated radiation patterns, is a good way to get in your mind. And you can even take Google Earth and cut this out, and you can lay this down. You can lay the pattern down on Google Earth, and then you can follow the lines from the pattern to what countries, and really teach yourself how your antenna is going to work in the States, which states you're going to get. A specific example for me, because I was an ignorant person. When I started, I put up a 40 meter dipole after I had elevated my vertical. And I had many conversations with people from Pennsylvania, Maine, you know, along this axis, okay? I just had, not once in a while, not too long ago, I had an FT8, honest to God. So my antenna is oriented in this direction, which sort of points north. Japan is over here off the null of the antenna. So the lowest gain is this side. It's not zero, but it's some teeny little gain. About 6 weeks ago, I was using FT8 one morning, and a Japanese station came in on FT8 on the side of my dipole, no lie. But it's not, that doesn't happen very often. However, I get Europe routinely, I get Mexico, all with this nice little dipole. At any rate, this actually quantifies the gain because on the left side, these colors are associated with numbers. So 6.72 dBi here. And then as you get down into these blue regions, it's minus 23 dBi, the dark blue regions. and minus 4.3 dBi. So you're not going to get too much activity off the lobes. But I was doing great with Pennsylvania, and I read about OCFs, and I decided I wanted to build my own 4-to-1 balun and build an OCF. So I built one weekend. I built the balun, ordered all the little magnetic stuff you need, built the whole thing, checked it with my impedance, and it actually worked. It took 200 ohms of resistance and brought it down to like 53 ohms, 52 ohms. So success there. I put wire on it and I put it up, and I scanned the SWR with my meter for the actual, and it was phenomenal. You can see the SWR for the OCF on my QRZ page. If you go down, it's just, the OCF is just a phenomenal antenna because you get 80, 40, 20, 17, 12, 10, and 50 megahertz. And it's unbelievable band access for like $50 if you build the balun yourself. If you buy the balun, you pay a lot more. Or if you buy the antenna, you'll pay hundreds of dollars. But if you build it, you'll be in the $60 to $70 range. And so I put the OCF up, and I was so happy. I saw all of this awesome SWR across all these bands. And I went to 40 meters, and I rarely got Pennsylvania. Whereas before I was contacting this one guy in Pennsylvania routinely, I could never get him. And I just had no idea what was going on. And later on, I'll show you guys what was going on and what the OCF does to this pattern when you put it on 40 meters in this orientation. Okay. So those are the two main methods of analyzing your antenna graphically. Now, let me show you how to do a frequency sweep. So first, well, you hit F7. And now you can do, once you build the model, if you do the frequency sweep first before you build the model, it won't work. You have to do that first. Now, if I do a frequency sweep, let me just make sure I got a reasonable. We'll go from 13 megahertz to 15 megahertz, which will cover 20 meter band. I'm going to do 0.05, which is a fairly dense set of slices. And
Mike?
Yes.
Yin has a question.
Yin, go ahead.
I think I played around with the interface a while, and I am only in that window that you are seeing the total gain. Unfortunately, I'm only seeing like the horizontal or vertical electric fields. How do I see the total gain?
Okay.
That was in a 3D viewer.
So,
or are you in the 2D?
You mean in the 3D viewer?
Both. There was a 2D, and you were able to see the gain. Well, can you just run through the steps about how to see the gain?
Sure, I'll start from scratch here. So I'll use the UI this time. All right, well, I'll use the UI. First, I'll generate a far field pattern. So I go to wherever I went to, so calculate neck output data, far field pattern. I first do that. Now, you just see one little, do you see this view?
Instead of that view, I see the electric field, and I can rotate between the horizontal and vertical planes. So it does not show me total gain.
Can you do me a favor? Can you just close Fornec 2 like that? And then from your icon, oh, let's do one other thing, Yin. Do you know how to use the command prompt on Windows?
Yeah.
Great. So go to this directory. You have the C directory on your Windows as your install directory for Fornec 2? Did you just do a default install of Fortinet 2?
think it's somewhere else, but yes, I know
So
where it is.
if you would, so there's something important. If you would go to wherever you have installed, actually just go to C:\Fortinet 2. It should be there, no matter where you installed it. I'm not 100% sure, but try that.
Okay. Yep. I think it's there.
Now, look in that directory. Is there anything in there?
Yep.
Okay, very good.
Yeah, it has the same files that you have.
Okay, good. Now let's go to a directory called out.
Mhm.
Does it have anything in it?
Yep.
Okay, however you want, without goofing up your computer, delete those. Are you sure you're in this directory?
Yep.
Delete star.star, as long as you're 100% sure you're in this directory.
So I should delete everything?
Everything. In out,
Okay.
as long as you're in this one directory.
Sure.
Let me know
Okay,
when
done.
you're done.
Done.
Okay, very good. Now, open Fortinet 2. So everyone, that directory, it holds a memory of what you've done in the past, which if there's an error in the program, it can actually disable you from updating and running, because as long as that error is out there, Fortinet 2 will come up with that error and you'll be hosed. So I delete that before I do anything. So now, Yen, let's go to calculate. NEC output data, far field pattern. And let me know when you get to that point.
Oh, mine, it checked surface wave. I think that's the difference. Yeah, okay, I see it now.
So you click generate, and now you see this view, correct?
Yes.
Beautiful. Now go over here to this little 3D thing up here.
Okay.
Click it. Now you're going to see nothing. You're going to see just the antenna. Now go here and select current. Now you'll see the current. And then where it says hide pattern, go to multicolor.
Cool. Yep,
You
I
see
see
it?
it now. Mm-hmm.
Awesome. Very well done. Okay. So those, now, Yen, did you follow over here where we rotated through the slices?
No.
No, I don't think so.
Okay. So it's okay. It's okay. I mean, I'm confused and I've been doing this for 10 years, right? Sometimes. So show, you come over here in this pane. Do you still have these two panes up?
Yes.
Very good. Go to this pane and select current magnitude. All right. And then go to show near far field and click that. Now rotate it like this so that you're looking down on it with the antenna horizontal.
Okay.
Okay, now go back over here to this screen and pick an angle, any angle you want to pick. Okay, I picked 65 degrees. And keeping the mouse focus on the left, reach down to your keyboard where you see the up arrow, the down arrow, the left and the right arrow, and press the right arrow one time.
Okay.
Did the red line move?
Yes.
All right, now do it all the way until the red line goes horizontal. And that's your entire pattern in that quadrant. Okay? And you can take data as a function of angle, as a function of the elevation angle, as a function of phi. You can learn everything you want to know about your antenna here. And I mean, if you're actually going to be doing a true science project, you know, this is all written out in these giant text files, but it's easier for me to just do this. Okay, so you saw how to rotate through. You've got a pattern that looks like this. Question, press I. Wait, put the mouse focus over this pattern and put this red line straight up at the maximum slice for gain.
Okay.
Now press I.
Okay.
Now tell me what it says for the dB in red.
6.65 dB.
6.65. So now tell me the frequency you're operating at.
14 megahertz.
14 megahertz. Okay, so the difference between my model and your model is a difference you've already highlighted, and that my model length is different from your model length. And that's the origin of the difference in these gains, okay?
Mm-hmm.
So
Yep.
now let's do one other thing. Calculate NEC output data. Let's do a frequency sweep from 13 megahertz to 15 megahertz. Are you there?
Yep.
So we want to do a frequency sweep, 13 to 15, and let's do a pretty dense one so we get a good look at where the minimum SWR is for my antenna. For your antenna, it's going to be different. And I'm going to ask you what it is. Okay, so here's my antenna. My antenna is currently actually tuned to be at the very bottom of the 14 megahertz band, and the minimum SWR is right there at 1.555, etc. So where is your minimum SWR for your antenna?
Hello?
14.4 megahertz.
14.4,
Stand by
perfect.
one.
Okay, so for the length you have, you're almost, well, so you're up near the phone band, and I'll show you how to tune this. So this is what I want to ask you to do. Sometime this week, because we're running out of time here, unless people want to keep going, but sometime this week, extend the left and right length of your antenna, and then redo this curve. In fact, I'll do it right now. I'm going to extend my antenna. I hate to do it. I should save a copy first. Okay, now if I screw something up, I don't have to redo everything. So I'm going to extend the length of my antenna on both sides to 5.5. And, oh goodness, minus 5.5. Where's my plus 5.5?
Wire 3.
On one, I got, hang tight. Why don't I see a plus 5? Oh, I'm sorry. Yeah. Whoever said it was right. Getting old. All right. 5.5. Thank you, wire 3. 5.5. All right. Now I have to run this model again. Now, I am going to do what I recommended you do. So I'm going to go to C:, just in case I got some trash out there. and I do, I'm sure, and I'll give you guys a better command next week. So now I don't have anything hanging out there that's going to result in this computer program after I've updated it. So sometimes when you update it, everyone, because that file is sitting out there, when you run again, you won't see a difference. You'll be like, what did I do? And you'll go back to the file and it'll be updated and it will be saved. And for whatever reason, Fortnite 2 is not recognizing that you updated the edit file. It's still seeing the old file. So now you killed the old file. So when you run this, there's nothing out there to say, oh, there's a past run and the new run is going to be the same or whatever. All right, so, and you see, calculate the data. Now we're going to do far field pattern first. And let's check the max gain. Whoops, dang. Sorry, guys. You actually have to put your click in the, all right. So 6.72, let's see if frequency sweep, same. And did I not save this? Okay, I see what I did wrong. So what should happen if I actually did this correctly is we'd be down around 13.6 megahertz. But because I made a backup file and then I edited the backup file because I'm getting old, we see the exact same thing I had before because we're running the exact same thing I had before. So do you guys want to hang on while I actually change it, or what do you guys, I can do that.
Mine works. I increased the length and it went to, I used your longer lengths. It's now resonant at 14 megahertz. So it's good.
Okay. So now you can begin to, you can see the relationship between length and the frequency. And the reason I tuned mine to be the bottom of the band is I want you guys to tune your antenna once your model runs to be on the phone band, which is up here around 4.4 megahertz, which is where you were before, you know. So some guys do CW only and they tune to the bottom of the band. Some people do phone only and they tune to the top of the band. And the reason for that is because the lower your SWR, the much lower your losses through the transmission line. So you guys want to keep going? Does anybody else want to, Yen, would you like to display and show everybody what I just showed you?
Wow, that's like calling me out.
Well, you're done.
Sure.
So
Sure.
I can, but if you're uncomfortable, I absolutely don't want you to not come back next week because I put you under pressure here. So it's okay if you don't want to do it. I'm totally okay.
Not be so well welcomed.
Paul, I didn't quite make it out.
Paul, can you repeat what you just tried to say? We see that you're talking, but we don't hear anything.
Oh, I can't get the pattern window up.
All right, hang tight. So let's do it together. Calculate from the UI. First of all, file open. What file are you looking at? Let's reload your file. So open your file that you've been editing that you think is ready to go. And I'll do it again. So do you see something like this? Oops, I opened the wrong file. So do you see something like this minus this stuff in the back? And minus this? Paul, if you're speaking, you're on mute again.
Oh, okay. Yeah, I have the geometry window.
And you have the antenna looking like this in it?
Yes.
Okay, let's go up here to calculate. Neck output data. Far field pattern.
Oh, I don't get all of that. Calculate what?
Oh, no problem. Are you able to see my screen?
Yes.
Calculate. Neck output data. Another screen will pop up, a separate screen, and select in the buttons on the left, far field pattern.
Okay.
Now click at the bottom left, generate.
And it gives me an error.
What does the error say?
Wire scaling in effect while using millimeters, centimeters, inches, foot suffixes. Metric dimensions are multiplied with both factors. So
I think that's more of a notification than an error.
Oh, well, I'm not sure. Let's see if that's true. If that's true, you should, do you see this screen?
no.
Yeah, you got an error.
Okay.
I get that too. Just click OK.
Well, then it gives me more definition here. It says tag 1 and tag 3 are crossing or not connected. So maybe I got to go back and tweak my geometry a little bit.
Right, so the geometry of the ends of each of the wires you have to be aligned exactly. So as we briefly talked about, in the left wire, we have minus 0.15, and then the center wire has to start at exactly minus 0.15.
Okay.
If you end this guy at 0.16 and start this guy at 0.14, they're overlapped and you'll get an error.
Okay.
So you guys screen snap this because this actually runs. And then you can replicate it. And let me know when everybody's done screen snapping.
Done.
Okay, everybody else done screen snapping? All right, now, I don't know how many people got completely to the point where they can run and they can see the results that we just went through. But if you did not, screen snap this guy, replicate it in Notepad++, save it, and then open Fornec 2 and go through some of the stuff that we did today before next week. That will be homework. Is that reasonable to request?
Absolutely.
Carl, what do you think? Is that reasonable?
Sure. Would it be possible for you to send me that file so that I can just send
Absolutely.
it to everybody? This
Yes.
way, we don't have to
So-
spend time entering this and making more typos.
Sure. Absolutely. So I have, what I'll do is I'll send you a Google Drive link with all of the course artifacts. and which will include all of the models that we're going to do.
Okay, I think I sent that drive link out with my email yesterday, so everybody should have that.
Yeah, so if you look in that Google Drive link, if you, assuming I didn't look hard enough to see that it was actually there, but that Google Drive link will have all of the models we're going to do, which are going to be derivatives of this. After we're finished with this, we're going to add a transmission line. And then after we're done with transmission line and understanding what it does to an antenna, we're going to change the frequency as if we're going to function on Mars, and we're going to leave the antenna alone and just change the frequency to 16 megahertz. And then we're going to, I'll show you guys how to use ForNec2's automated capability of generating multiple different kinds of matching sections. And we'll match this antenna for 16 megahertz, and then we'll build that network into this antenna. So that's what's coming next week. And all of these models are in this Google Drive link. You can actually run them, but I would prefer you not do copy and paste, because getting used to implementing the cards and the pain associated with it is really part of getting to the point where you can do the symbolic format, which is where the true power, I swear, the true power is. So if you can go through it, including all the typos, which I make and everybody makes, and then you'll be closer to being able to work with the symbolic format when we do that. And the symbolic format, there's only one place you can work, and that's Notepad or Notepad++, period. Which is why I'm not showing you guys how to do the easier stuff in ForNec2. There's, by the way, if you want to do the easier stuff, if you just, so let me show you. There's something called a geometry editor. Why didn't it come up? So now, this program. Okay, so now if I open this up with the geometry editor, well, sometimes the program just, I probably have to kill the existing file and do all of that, but let me try one more time. Geometry editor. Huh.
It works for me.
Yeah, it doesn't work for me. I guess I've used Notepad for so long, it forgot it has a geometry editor. At any rate, I'll have to figure that out, because in some analyses, the geometry editor is better to use than this view, because you get more detailed information from it. But there is, if you have, let me try a different one. HF beams, there's a whole bunch of existing models that come. So let's just pick this guy. It shows this view. Oh, this is geometry, but it's not the geometry editor. Well, I'll figure that out. Huh, that's weird. I never use it, so I didn't know it didn't work. So the geometry editor allows you to actually draw lines and do all of this. And for this kind of antenna, it'll take a few seconds. And then you can save it off, and there'll be a file out there. But you won't know anything about the cards that actually make it work, and you won't be able to ultimately transition to a more to the symbolic format, which is like writing code. And you won't be able to use the optimization and the genetic evolver, which are so cool. All right. So hopefully this wasn't too painful or dragged on a little too long for you guys. I hope you enjoyed it. when you first get started, it is a little painful to do this level of detail. But as you get used to it, it's much easier. And once we transition to symbolic format, you'll see why I started in this approach.
So Mike,
Questions?
if you stop the screen sharing, we can see everybody again.
Stop share. Ah, gotcha.
Okay, we can't really see anybody because nobody has their cameras on.
Well, everybody can see how ugly I am, so, but that's okay. I usually don't show myself either because when I see myself, I feel kind of embarrassed. But yeah. So what do you guys think about today's session? Was it, give me any negative feedback is actually more valuable than positive feedback. And I'm not sensitive. I've been in the research community my whole career. I got a shell hardened exterior. So what do you guys think? Brian, you're on mute. You guys got to unmute yourself.
I was going to say I've played with this before, so I've had a leg up. But even while we were doing this session today, I stumbled a time or two. So I'm happy to report that I got my model to run, and you know, it looks good.
All right. So if I can ask, I know Yin got hers to run. I bet Carl, I'm sure Carl got his to run. Peter, did you get yours to run? You're on mute, Peter.
No, I'm still struggling with getting the cards. I didn't make the cards, so I got to go back to Notepad++ and get that working and build the cards and run it. I think I got the right data though.
Well, Peter, this is what I would suggest to speed it up. Go to the email where, and maybe Carl's going to send it again, I'm not sure, but go to the email that he sent out, and there's a link to a Google Drive. And let me show you what's at that Google Drive or what's down inside it. So, oops, that's the wrong one. Antenna. So inside it, you're going to find this guy right here. Here's the file name you're going to want to open.
Mike, you need to share your screen again.
Oh, thank you. My apology, guys. Okay, can you guys see my screen now?
Yes.
Okay, so when you go out to the Google Drive, you might want to jot this guy down. There's a bunch of models in here. I would prefer you not go ahead. But all of the models we're going to cover here are currently here. And we may, I'm hoping we're going to have time to do a beam and then a shortened beam with a coil. Because if you can do all that, you can do everything. So open this model. If you just double click on it, it'll come right up. And then edit, input. Oh, now I got the geometry model. All right, hang on. Settings, notepad, edit, input. And this is what you'll see. Now, don't just use this because that defeats the entire purpose, because eventually we're going to build this into in a slightly more complicated way that gives us much more power. So take a look at this and do the typing and looking up of the cards for those of you who didn't get it to run. And ignore these, remember these CMs down here are comments. I'm going to do that next week too. And go ahead and build your file until you get your own file to run. And that will slowly build in the true capability that I want to impart. Okay, but this you have access to, so you ought to be able to get it to run pretty quick. But please, I do request that you go ahead and do the typing and the pain to build your own file. You can look at this file But ideally, you would look at your drawing and translate your drawing into the wires. And then you guys may not have, no, you have this too. So the antenna modeling thing, ideally what you want to do is look at this and build the template around this until it works. And that way you'll, the next time you do it, you got to have a wire card, you got to have a scaling card, you got to have an end card, you got to have a ground card, unless you want to do free space. But I'm not even going to bother teaching that, because there's no such thing as free space unless you are doing satellite design, and we're not going to do that. So that's my recommendation for work this week. Take the one that works, look at it, put it off to the side, use this and finish your work to get this guy to run, knowing that this is a template.
Joe has a question.
Hey, Mike, just on the elevation of the Z, I noticed you had a 9.44 for all three of the wires, and then the G4 is 9.34. What did the 0.1 difference?
Good question. So I had mentioned that you need to raise the mast up off the ground, and you need to offset it from the antenna, because NEC does not support connected wires. It doesn't support connected wires like that are orthogonal.
Got it. So that's actually 0.1 meters lower than the actual segment 2, center of
Correct.
segment 2. Okay, got it. Thank you.
Yeah, that's just, you can try and see what happened. You're going to get it, but you will get.
I get an error. Yeah.
Yeah, you'll get an error.
Yep. Thank you.
No problem. So what that does is it enables you to basically simulate a mast and an insulator from the mast, right? Because you wouldn't necessarily hook this thing straight up to a metal mast. You would build your dipole around an insulator, and the insulator would touch the mast. So even in real life, your mast doesn't actually connect up with the antenna.
Great. Thank you. That helps.
No problem. Thanks for the question. Other questions? So everybody get your model to work, go through the pain. I was actually working back when I started learning this. It's worth the time, at least for me, and what I was trying to learn about antennas, it was worth the time spent, because over time you can begin, like, I'm with the RDXA. We have all kinds of questions about antennas. I have a guy that wants to put up an inverted L. Can I help him out figuring out what's the optimal this, that for his trees? Another guy wanted to build a shortened beam, and he wanted to build it out of wire and hang 2 different wires and 2 different trees, and he wanted to shorten it because blah, blah, blah. So we did that. I've even built for someone a dual dipole. This was really cool. It took a long, it's easy to do once you know how to do it. A dual orthogonal dipole like this, that's perfectly omnidirectional. And you guys might know that in order to do that in real life, you have to do 90-degree phasing with a quarter wave bit of coax, and then you'll get an omnidirectional result from 2 crossed half-wave dipoles. But to do that in NEC too, which is possible, you then have to have real and imaginary components to the exciter, because when you feed a real system, you have one feed point, and then you have a length of coax, that gives it a 90-degree phasing. And the way you do that in 4NEC2 is with real and imaginary components. And that's the first time I ever used real and imaginary components. So, I mean, there's so much power here. That's it, my little sales speech for the work necessary. So how many of you guys coming back next week?
You know, it's interesting because I guess I had put it on my calendar as a monthly as opposed to a weekly. So,
Oh, yeah, it is. I guess it is supposed to be monthly. Yeah. So, you know, I'll talk to Carl, see if he wants to do it more frequently, or maybe a month is the right. Maybe a month probably gives you guys more time.
and I'd be happy to help out anybody who seems stuck. You know, we can have some, you know, get-togethers at different hours.
Yeah, me too. I mean, if you guys want to work on it, if anybody gets stuck on their model and just can't figure it out and they're getting error after error, just email me and we can set up something. An alternative is you do have access to the actual model that runs. If you work in Notepad, you can open the one that works right next to the one that doesn't and start working your way through until you find the error in your own model. So let me just, for those of you who haven't used Notepad++, I've got it on my desktop here someplace. Here we go. So I've got this one model and I'll load another model. And in your case, you would load this one. And oh, what happened? Oh, I loaded the exact same thing. So let me load something different. Okay, so now I've got two models side by side in NEC2, in Notepad++. Here's the one that works. Here's mine that's got a bugger someplace. I can go through and look at it. I can't find it. I come over here and compare it to this one, which works. And boom, oh, I see. Okay, so if you use Notepad++, it should be easy to debug if you have the actual model. Okay. So that's probably that's probably okay for today. What do you guys think?
I've got one question, Mike.
Sure.
I'm going to want to build a geometry for a horizontal loop. And I've got horizontal sections that meet at 90 degrees. Do I have to put a little stub in there at each of the corners?
So let me, 1 second. Let me show you guys something. Oh, I got to share my screen. 1 sec. So I'll show you something that's pretty powerful. It's not. So 4NEC2, when you install it, well, let me find it. It comes with a set of models. I've moved them to here. So when you install 4NEC2, it comes with all of these models. And you might actually find a loop in here. So this is the place to start. Now, the amazing thing about 4NEC2 is it also reads the EasyNEC files that are put out by EasyNEC in .ez format. It's a binary format, but somehow this guy decoded that binary format, or the owner gave him the binary format. I don't know. But I have all of the, so here's all of the models that come with 4NEC2 when you install it. If you look around, you'll see them. And there might be a loop in here, I don't know. Fractals, aperiodic, rhombic. Let's see what that one is. You can see. Anyway, you can get, let's see, is there any average? So take a look in your install folder for these and see if you can find already a loop. A loop is a pretty common antenna. I don't know what would be here. Maybe not. I know there's a helical one, which will answer your question. I just don't know where it is. It might be one of the easy neck ones. So let me, just 1 second. Let's see. Are they under here?
I am finding a loop under HF simple. There's a loop circ 20, and there is a delta loop on the ZZ mini neck, HF multiband.
Okay, let's take a look. But there you have it. So
I
the
think
answer,
I think Paul is looking actually at a different loop. This looks like it might be more of a magnetic loop.
well, I think Paul's question is, what do you do at the joints?
Hmm.
And the answer, depending on how big the loop is, this is not an acute angle, right?
I'm looking at a horizontal antenna that's 140 feet on a side with a right angle at each corner.
Okay, right. So the acute angle, hang on. So I'm not so I don't know where the angle is that's too acute to be, start giving an error. In our case, we don't even have an angle. We just have to have a separate piece in the middle for the EX. And here you can see that whoever built this model, and this model was probably built by, let's look, CBIC. No, CBIC always signs his. Some of the ones that are in here are from CBIC. So I don't know who did this one, but they clearly thought it was okay. So the way that you can tell if you're too acute is build the model with your acute angles, run it, and then put little stubs in between that make it less acute and see if you get a profoundly different result, in which case you're too acute. But for a loop, I think it'll be fine. And you can start with this guy right here and just modify it.
Okay.
Which is absolutely the right thing to do.
Got a month to try it.
Oh, and look, you will also have to be familiar with the symbolic format to do this one. So this probably was either CBIC or it was Ari Boer's, because this symbolic format is not exactly widely used. But these guys used it routinely. It's used so Fornet 2 is actually used in universities as well. And the kids at the university can do it. But in the amateur community, it's not widely, the symbolic format is not like everybody's doing it. Carl, thanks for finding this.
You're welcome.
Other questions? And I'll talk to Carl if he wants to do one that's less spaced out, or if that's just the way we should do it, because maybe we're going to exhaust people or lose them. So, yeah, but
Right. And this is how we scheduled it in the beginning, and everybody now has it on their calendar. So I think we should stick to that for now.
Okay, we will.
If we find out that after a month we lose too much of what we learned today, we may have to come up with a different way of doing this. But for now, I think we should stick with the monthly pattern.
So I agree. And one thing I would ask all attendees, though, is in the month that you have, take today's model and make sure it runs. You saw some results. You already know what a dipole should look like. And play around. Once you get it to run, play around, look at the far field pattern in the one view, look at it in the 3D view, do some sweeps, become familiar with the mechanics of the interface and what it can tell you before we meet next time, because next time we're not going to work on this model. We're going to take this working model and we're going to add a feed line, and then we're going to see what a feed line does to a dipole. And then after that, hopefully that'll go quick, and I'll show you guys how to build and implement into the model a matching section that makes it resonant, this antenna resonant for 16 megahertz. And once you do that, you can build any kind of matching section on any antenna you want. So hopefully that's what we cover next time. All right.
Good. If we don't have any questions, I think at least I'm hungry. Let's meet in a month. Thanks everybody for joining. Thank you,
Yes.
Mike, for doing this.
Thank you. And if you do have any feedback where I need to do something more effectively or whatever, feed that back to Carl, and he'll, if you call him up and you rant and you say, man, what is this guy doing? Blah, blah, blah. He'll clean all that up and he'll say, Mike, you need to do this better. So if there's any feedback, just contact Carl, let him know. And negative feedback's good, because I've not done this kind of format before, and I don't know what works and what we should be doing. I'm doing what I think we should. Anyway, that's it.
Okay.
Thank you for attending. I
Thanks
love this
again.
stuff.
And
Thank you, Mike.
Thank you.
All right, thank
Carl.
you guys.
So Karl Heinz, you said you're hungry, but you're not thirsty yet.
I have water. That is
There's a
taken care
reason.
of.
Water, huh? That's why they kicked you out of Germany for drinking too much water.
Okay. Bye-bye.
All right, take care, guys.
Y'all take care. Thanks a lot.